Good morning, everyone. Bonjour tout le monde, or greetings wherever you are. I understand we have folks with us from all over the world. So thank you all for joining us at our lecture today. I'm a member, my name is Fadi El-Masri. I'm a member of the Royal Aeronautical Society's Montreal Branch Committee, and it is my distinct pleasure to be the MC for today's lecture, Perspectives on Aerodynamic Drag. This lecture is co-hosted or co-sponsored with our friends over at the Canadian Aviation Historical Society's Montreal chapter, and it's also very special to us as it is being presented by the Montreal branch's own chair, Dr. John Maris. So gives me distinct pleasure to be the MC for today. Just a couple of housekeeping items. This lecture is being recorded. You'll notice there is a chat function that you may ask your questions. We'll have some time at the end for a Q&A period, so please feel free to ask your questions as they come up during the lecture, and we'll try to get to them as many as possible. Without further ado, it gives me great pleasure to introduce Jim Mason, who is the current president of the Canadian Aviation Historical Society Montreal chapter. Jim began his interest in aviation as an aircraft spotter during his early teens at the Dorval Airport. At age 15, he started his own aircraft washing business and was later hired by Executive Aviation as a line boy, eventually working as an apprentice mechanic, flight dispatcher, and pilot. He joined Air Canada in 1972, and after retiring with 36.5 years of service, he flew worldwide flights with Portuguese charter airline. As a certified aviation auditor, he has consulted airlines for their IOSA safety audit renewals. For over 25 years, Jim has lectured with the Washington Airlines Society, the FAA, the Smithsonian Air and Space Museum, and the Canadian Aviation Historical Society. It gives me great pleasure to welcome Jim.
Thank you, Fadi. First of all, on behalf of the Canadian Aviation Historical Society, the Montreal branch, we'd like to thank you and the Royal Aeronautical Society for the partnership and sharing the platform with us. For our members from CHS, there was a different way for you to sign in, and the reason we did this, the main reason is we are limited to 100 people on our platform. So by the Royal Aeronautical Society being nice enough to let us share on the platform, we're able to have a much wider audience for people to come. And I believe now, just outside of our association, I believe we have the FCASI, the Canadian Aeronautics and Space Institute. We have RAPCAN, the Retired Airline Pilots of Canada. We have the American Institute of Aeronautics and Astronautics on board, and also the Washington Airline Society, the WAS with us. So I think with this cross-mingling of organizations, we all have common goals, and to help promote the aviation industry and hopefully to attract new members, especially the younger group. And I think we all, beyond our specialties in our organizations, I think this is one of the things that we're really looking forward to do. For those not familiar with the CAHS in Canada, we have it's a national group of one national group that oversees and is the actual charitable organization. Other than the national, we also have 10 chapters. We have 9 physical ones all across Canada. And this year, or last year, at the end of the year, we had our first virtual chapter. And this is interesting. It's the Canadian Aerospace Artists Association. And they are famous artists and painters of aviation drawings. And, and these people are just as crazy about aviation as most of us nerds are as well. So it was nice to have them on board as well, because our local chapter is we have quite a varied cross-section of members. In other words, we're not all engineers or pilots or, executive of airlines. We have just normal people who are interested and crazy about aviation. And so this is what we try to do as it goes. And just for our CAHS Montreal ones, just a reminder, next March, March 18th, the normal time, 11 o'clock, our next speaker is going to be one of our members, Doug Seagram, and his topic's going to be From Bush Pilots to Boredom. And it's a story of his dad, Herb Seagram, who many of you probably know as a Canadian aviation pioneer. He started in the early 30s from a maintenance helper to a bush pilot, one of the original TCA pilots, and right up to top management at Air Canada. So we hope anyone who's willing to join on that, I'll be happy to send a link to that one as well. So that's all for me. I just want to introduce you to John Maris. Now, John, as you know, he's well known by many aviation and aerospace organizations, and other than being the chairman of the RAeS in Montreal, I mean, I could go through all his fellowships of the CASI and the Society of Experimental Test Pilots, and he's an Aviation Week in Space Technology laureate. But the main thing is he was inducted into the Canada's Aviation Hall of Fame as well. And like I say, on his private side, he's had a PhD in aviation safety and human factors. He's still a practicing aeronautical engineer, and I believe still does test pilot work, as well as running his company Marinvent, which does aerospace consulting and training and flight test and research and God knows whatever things he dabbles in. So, but to us in Montreal, he's a very loyal CAHS member, also with his wife Julie, who attend as many meetings as they can. He's a frequent lecturer with us, and I think the biggest thing I can say is he has an ability to take a very technical subject down to the level of his audience, which is, so any of you, from our chapter especially, don't be afraid when you see an engineer's formula on there on a slide, because John will smooth that all over for you. So in the meantime, I'll pass you back on to John, and we hope you enjoy your presentation today. Thank you.
All right, Jim, Fatty, thank you both so much. Just a quick microphone check before I talk for an hour to myself.
Yeah.
Okay, looks like we are live. So welcome everyone. We've got folks from around the world, so whatever time zone it is, good evening, good morning. Thank you very much for your attendance today. The first slide, which hopefully, again, give me a thumbs up, Fatty. You can see my first slide off my PowerPoint. Excellent. This has the original title, which was A Brief History of Drag. And then we realized early on that we were getting about half the signups from non-aeronautical folks. And we realized that we had to be a little more specific into what we were talking about, so we didn't bitterly disappoint half of the audience. So this is not that kind of drag, it's the aerodynamic kind of drag, and that's why I changed the title to Perspectives on Drag. So apologies if you're in the wrong crowd. And speaking of crowds, the lecture is a combination of history and some engineering, as Jim pointed out. I don't know if I can smooth the formulas out or not. But it's a good time to decide which faction you're on, which team you want to be on, because that will help you decide when to go and refill your coffee cup and take bio breaks and so on. So you can see the slides as they come at you and decide which one suits. So I'm going to see if I can exercise my engineering skills and get to the next slide. No, that didn't work the first time, so we'll try it the second time. Okay, so this is the first of the technical slides. I hope I don't lose anyone at this point, but this comes from a group called lefthandedtunes.com, and each of the slides has the sources. So if you ever want to know where I picked these up from, most of these are public domain slides, and the references are on the slides themselves. The claim to fame here is they draw all their pictures with their left hand, and they're right-handed people, but I think it does capture almost all of the topic material for today. We see the air hitting the airplane. Some magic happens at the front, some important magic happens in the middle, and more magic happens at the very end. And the end result is the airplane flies successfully. So we're doing a speech on aerodynamic drag. Let's find out what we mean by that. One definition from NASA Glenn, I'd like to use high-powered sources, is aerodynamic force that opposes an aircraft's motion through the air. Okay, fair enough. So Here's some aerodynamic drag in action. This thing is actually flying. The parachute is clearly not helping it fly, so that's aerodynamic drag. We have to be a little bit careful because sometimes what looks like pure drag is not drag. If you try and define which way the seat is trying to go, that parachute is providing almost as much lift as it is drag in the direction that the perpendicular to the vector of the seat. So that's aerodynamic drag. I thought I'd include this slide because I just love this slide. This is a real aircraft, and Kalula Airlines effectively, I think, means no sweat, and they have a series of these things. They have arrows to point to where the pilot should get into the airplane and which way is up, which is the left engine, which is the right engine. I think that's a very promising airline to fly with. I like that. I'm not affiliated, so I can say that. One of the key points about aerodynamic drag is just how long we've known the important material, the important science behind it, and just how long it took us to apply that successfully. So let's have a look at a few people and some dates. Everyone's heard, or anyone in aeronautics has heard of Bernoulli's theorem. It was published in Hydrodynamica in 1738, and we'll see the theme that recurs. Bernoulli wasn't the one that published Bernoulli's equation. It was published by Euler in 1752, and there's enough there to more or less design any sort of subsonic airplane. A gentleman by the name of Claude Louis Navier, with his colleague George Gabriel Stokes, derived a pair of equations called the Navier-Stokes equations of motion for viscous flow. The date is 1845, I don't know, 60, 70 years before the Titanic. These equations effectively fully define what viscous flow will do, and we'll have a look at them in some detail a bit later on. 1845. Mr. Stokes was actually prolific, and he discovered another concept, which Mr. Summerfield decided to name Reynolds number after his friend Osborne Reynolds, who published it in 1883. So it took 30 years for Mr. Reynolds to publish Reynolds number, which wasn't his invention, it was George Stokes' invention, publicized by Arnold Summerfield. So you can see the path can be somewhat tortuous before we get to the end. But Mr. Stokes did actually come up with Stokes' law, which is the metric system kinematic viscosity measure is called the Stokes. So he did get his claim to fame. All right, let's talk about these Navier-Stokes. I know all the aerodynamicists are dying to address these things. So here they are. You can see it's a fairly straightforward continuity momentum equation. And as you can imagine, the terminology is standard. We have V bar is divergence, V bar dot U is expansion rate. And we can expand it relatively simply into this form, where we introduce zeta, the second viscosity term, volumetric viscosity, and then of course there's a hydrostatic term on the end. Pretty straightforward, as you can tell. No, I'm just kidding. If you can solve this, the Clay Mathematics Institute has $1 million for you. It's been characterized as one of the most difficult mathematical problems to solve. And without gross simplifications, we don't even know what domain there's a solution of these equations across. What they do is they fully define what the speed of a particle will do in viscous flow, and viscous means sticky. Think of treacle and honey as opposed to water. And they ideally will give us the complete aerodynamic solution for every particle of air, if only we could solve them, but we can't. All we can do is make a bunch of approximations and then try and model around those. I just read a paper about someone solving these equations for air flowing over a surface with a step in it. And that's how much it was simplified. These are the basis for all of our computational fluid dynamics, effectively, the many forms that these equations have. Now let's get back to our main topic, drag. What kinds of drag do we talk about? Well, we have parasite drag. That's composed of form drag, sometimes called profile drag, which is drag arising from the shape of the thing that you're flying around. Part of the parasite drag is skin friction drag. We'll come to that in just a moment. It's self-evident what we mean by that. Interference drag is when we have two components, such as a wing and a fuselage, butting up against each other, and the airflow doesn't know which way to go around that, and that tends to cost us in drag terms. We have wave drag, which is as a result of the formation of shock waves. It happens anytime an aircraft is transonic, which is where no matter what speed the plane is going, some part of the flow achieves sonic velocity. And then we have induced drag. Induced drag is drag caused by the production of lift, nothing else. Just if the wing is lifting, you have induced drag. So there's our drag story. We're going to look at each of these in turn. So parasite drag is everything except induced drag. As we said, it's profile or pressure drag. It's caused when the boundary layer is the thin film of air adjacent to the surface we're interested in. Effectively, it's as thick as from touching the surface, where the air doesn't move relative to the thing we're looking at, all the way up until the air reaches the same speed as the sort of surrounding airflow, not affected by the skin of the vehicle. Boundary layers can be almost invisibly thin, a millimeter or two, or they can be inches thick, depending on the situation. Interference drag we've discussed, and skin friction drag we're going to look at next. I know that I said I promised to talk about the space shuttle and this skin friction from re-entry. We know the space shuttle does whatever it is, 17,500 miles an hour, Mach 25, and it gets very, very, very hot because of skin friction. No, it doesn't. Skin friction has very little to do with it. I think the easiest way to deal with this, I'm hoping, Fatty, give me a thumbs up for the cursor over the fuselage here. Yeah, okay. So let's imagine that the air was a series of small sanding blocks like you would use in your workshop. And we're going to take one of these sanding blocks at the nose of the vehicle and just scuff it all the way down until the very end of the vehicle and then just taper off at the back. I think it doesn't take much imagination to realize that the sanding block should be getting hotter and hotter and hotter as you keep scuffing, so that the hottest place you would see is at the very back. Right? We start sanding and it gets hotter and hotter, and we keep sanding and it gets hotter, and at the end the block is very hot and everything should be smoking. Of course, that's not what we see at all. On this thermograph, we see that what seems to be the hottest is the leading edges, the fronts of the wings, the tip of the nose of the vehicle. Where the air is really blasting by doesn't seem to be very hot at all. I mean, the fin should be seeing uncontaminated air at the maximum speed. I mean, think about it. If it didn't, the fin wouldn't work, right? It wouldn't have an aerodynamic effect if it wasn't seeing a lot of airflow. But it's cool. It's absolutely cool. So skin friction doesn't seem to be the culprit, and part of it is because the space shuttle, even at Mach 25, isn't seeing most of the dynamic pressure that it's flying through, and we'll see why in a moment. Let's look at a couple of statistics. About 80% of the heating is caused by adiabatic compression. Adiabatic compression is when you don't add heat from the outside. The classic example that everyone gives is the bicycle pump. You pump up your tire, the tire gets hot. Why? Because you're doing work to compress the air, and that work shows up, it manifests as higher pressure and higher temperature. So the space shuttle is effectively pushing a wave of air in front of it, which is causing the air to be compressed and hot. It also causes shock waves, which we'll see in just a moment. But that's 80% of where the heat comes from. And to give you an idea with a little bit of math, obviously the superheated air can actually break down the molecular bonds in the air and conduct and convect to the vehicle. Viscous friction, which is the, as I said, the stickiness of the air, does actually heat the atmosphere, but it's long after the space shuttle has gone by. It's all the turmoil amongst the molecules, exactly like when you stir a liquid very fast, it gets hot. That's what's happening there, but it's not what's affecting the space shuttle. So in actual fact, a study by Alan Eggers in '58 showed that the heating varies inversely with the drag coefficient. What does that mean? Well, we'll have a look at that in a second. This would be an Apollo capsule coming back in, and of course, it's rather easy to tell. It's the wrong end that's facing forward. It's the non-streamlined end that's facing forward. And what happens? This vehicle is, if you can't see it, is going from your right to left. And what happens is a shock wave forms in front of the vehicle. I'll explain shock waves in a minute. But the bottom line is the shock wave, a normal shock, which is a shock wave in front of a very blunt object such as this one, the flow is subsonic behind the shock. You can see in this thin layer in front of the vehicle, the flow is subsonic. And in fact, the irony of a shock wave is the faster the flow is in front of the shock, the slower it is behind it on a normal shock. So we get by a lot of the, quote, friction and other effects that we'd be worried about by putting a nice fuzzy shock wave in front of our blunt vehicle. And we don't then have to deal with the air cannonballing past the vehicle. It would be a much more difficult problem to solve if this vehicle was facing the other way and the triangle was facing forward. Now, you can tell that Rockwell, when they designed the space shuttle, went to extraordinary lengths to streamline the vehicle. No, they didn't. In fact, they haven't tried at all. If you look at the space shuttle, it is full of protuberances, tiles with edges on it, bumps in the cockpit. Looks a bit like a Vickers Viscount, if anyone's familiar with the Viscount historically. You've got the OMS, the Orbital Maneuvering System pods at the back that are just strapped on like a Lego accessory. The wing has this DC-3 aerodynamic profile. There's almost no effort at all to streamline this thing. And if you wonder if there are any more streamlined vehicles, I'll give you an example of what this would look like if you tried to streamline it. That's a train. This is the Shinkansen Japanese trains. And I think these exhibit what it looks like when you actually try and streamline a vehicle. And ironically, why is this? These things are seeing the same airspeed as the space shuttle sees when it re-enters, the same actual dynamic pressure as the space shuttle sees. I hear groans from the crowd. That can't be right. Well, let's have a look at some space shuttle numbers. The target velocity is 290 knots, equivalent airspeed. Just think of that as the airspeed that the space shuttle feels. Now, well, how can it be so low? Well, there's a couple of reasons. One is, as I said, there's a shock wave that slows the air in front of the space shuttle as it's re-entering. And by the time it's subsonic, it really is seeing that low an airspeed. And part of the reason is because the air is very thin up there. So when you're at 40, 50,000 feet, even if you're going quite quickly, the dynamic pressure you feel that pushes against you, that causes the drag, is equivalent to being doing 290 knots down low. The flight control certification limit for the space shuttle, my understanding is about 330 knots, and 470 knots is like, oh my gosh, 500 knots is as high as the airspeed indicator reads. As a contrast, the Tu-95 Bear turboprop bomber can easily match these speeds. So you have to adjust your perspective when you think of a space shuttle, not only from the frictional point of view, but in terms of the airspeeds that it's actually seeing. And if you've ever wondered why this thing is so unaerodynamic, in fact, the thing can have no wings at all, and they only really come into play during the flare maneuver and the landing. The rest of it you could do as a lifting body and just ignore all the rest of the aerodynamics, more or less. They certainly play no part in its ascent to orbit. In fact, the control surfaces on the wings during the shuttle's ascent, most of their effort is to try and relieve the wing bending moments so that they don't break the wings off. So the surfaces actually move not to control the vehicle, but to reduce the flexing on the wings as it ascends. Back to our historians. So the aerodynamicists can go and refill their coffee at this point. The Wright brothers wind tunnel here. A 30-mile-an-hour wind tunnel, 1901. You get an idea of the scale because they conveniently provided us the bicycle wheel, and it also historically, the context, of course, they were bicycle makers. Amazingly prescient to come up with a wind tunnel. We take these things for granted, but there weren't wind tunnels in that era, and they not only invented the airplane, but they invented the technology to invent the airplane. But it leads to some problems. I'm going to go back to the aerodynamics for a moment and look at the drag equation. It's not complicated, and we'll just spend a moment on it. Unlike the Navier-Stokes that I was kidding about, this is relatively easy. D is our drag, and drag is a force, so it's measured in force units, whether it's newtons or pounds force, depending on which part of the country or which country you're in. Rho is the density of the fluid, so the air density, the atmospheric density. U is the velocity, U for velocity, right? Not V. We use V for something else in flight testing. We use UV and W, and they're not the way you'd think. So U is the velocity. And as you can see, there's a squared term in the middle. So double the speed, 4 times the drag. And in fact, power depends on the cube of the speed because of the relationship between power and force. So if you want to double the speed, you need 8 times the power. That's why you don't see a lot of supersonic propeller airplanes out there. S is a representative area. Typically, we'll use the wing area. And CD is a coefficient of drag. What is it? It's the magic that makes the formula balance. And it's a function of this Reynolds number, which we'll come to. We'll take just a moment to have a cigarette, if I can make this work. What you're seeing is a smoke plume coming up from the bottom of a cigarette, and you can see that it's straight as an arrow as it starts up. It's ascending by convection. It's hot, so it goes up relative to the rest of the atmosphere. Notice how it's laser straight. By the way, if this was a tap with water coming out of it, it would have the opposite effect. It would start pouring straight, but look what happens here. For no apparent reason, the flow first starts to get wiggly, and then it breaks up into these vortices. What you are seeing, if it were a boundary layer next to an airfoil or a fuselage, is a transition from a laminar boundary layer, which is a straight bit on the bottom, to a turbulent boundary layer, which is the connected oscillating bits halfway up, to a separated boundary layer, which is all these turmoil vortices that you see up high. And for a given air density for, okay, sorry, that was just the add at the end of that. For a given air density, the transition between the laminar, the turbulent, and the separated flow is strongly a function of Reynolds number. And basically, if you think of a wing, the airflow starts flowing over the front of the wing, generally in a laminar way. Doesn't hang on laminar very long, usually. It becomes turbulent, the boundary layer becomes turbulent, but still attached to the wing, and then it eventually separates towards the back of the wing, and that's what we have. So let's have a look at Reynolds number. Again, a very simple equation. The point of Reynolds number is it has no units. It's just a number like Mach number. You can see some familiar terms already. By now, you're all instinctively aware that U stands for velocity. There's our rho again for the density. D is a dimension. How far back on the airfoil is a typical dimension? And mu is our viscosity, the stickiness of the fluid. All right, why am I bringing this up? First of all, let's take a look at some Reynolds numbers. The aerodynamicists have these instinctively. So your housefly has a Reynolds number of about 100 as it's flying. Why? Because it's flying in a sort of sea level atmosphere with very tiny dimensions. And you saw that one of the aspects of Reynolds number is just that dimension, the D in the Reynolds number equation. Honeybee goes up a little bit because it's a bit bigger and a bit heftier, and the velocities are quite high for honeybee, and the atmosphere stays the same. When we move into an airplane, a little airplane, we're up into the million and change range of Reynolds number. Airliner, depending on how big and how fast, you're up in the billions. So let's have a look at how nature handles Reynolds numbers, and then we'll see what the effects are. Here's a dragonfly, and it's operating at those tiny Reynolds numbers that we set up, the order of 100. What you notice is the airfoils on this thing are flimsy and thin, and nature has a way of coming up with the most efficient solution. So this obviously must work as well as anything else. And the bumblebee has these thin, wispy wings as well. This is what a vehicle that's designed for low Reynolds number looks like in flight. Now, there's a couple points I want to make here. One is, notice the thin, wispy wings. Notice the incredibly slow velocity. This is not a hot air balloon, right? This is an airplane that's apparently floating in air. It doesn't seem to obey the sort of equations that we would expect it to. You can see that another consequence of building an airplane like this is structurally, it's a disaster. It's flexing and bending. In fact, the first time we tried to fly this thing, it folded in half. But clearly, neither the propeller nor the wing or the tail of this thing are obeying aerodynamics as we would understand them. So, if I can just get to the next slide here. Sorry, it's just decided to do this as one slide at a time. Let me try it this way. So just give me a second. Can you see that full screen again? Did it change properly? Okay. So I had said in my little flyer that there's a misunderstanding that everyone made that set us back 30 years or so in aerodynamic design. And what do you suppose that might be? Well, I can see all the aerodynamicists' lips moving. Yes, it is the Reynolds number. Exactly right. What happened was when you build a wind tunnel like the Wright brothers wind tunnel, your Reynolds number is wrong because the dimension and the velocities are wrong, which leads you to a very low Reynolds number, which means the transition of the boundary layer, our smoke going from smooth to turbulent to separated, it's all done in the wrong place. Why does that matter? Because you start to build your airplanes with dragonfly wings, not with wings that work at higher Reynolds numbers. So this is an example of I can't remember if it's the Langley Aerodrome, and you can see Langley, after whom the NASA base is based in NASA Langley, is a very famous early pioneer. But you can see the thinness of the wings, dragonfly wings. Let's have a look at the consequences of that. This is a NACA. That's the National Advisory Committee on Aviation, I believe, 1915 through 1958. It was the predecessor to NASA. This is a NACA 0010 airfoil, 0012 airfoil. So it's a 12% thick airfoil. It's 12% as thick this way as it is along its chord. A pretty standard little airfoil. Why am I showing you this? Well, at very low Reynolds numbers, thanks to this paper from Winslow and Otsuka and et al., at very low Reynolds numbers, this foil flies better backwards than it does the right way around. It flies better with the pointed thin end forward. So see this little bubble on the front here on the bottom picture on the right? That's where the airflow is separated, and then it reattaches and behaves itself when the airfoil is flying backwards. When it flies in the direction it's supposed to fly, notice that this huge void of separated and possibly reverse flow back here means that it is hopelessly inefficient. So what do we see? This is a plot of angle of attack, which is the angle that the airfoil makes to the air, versus the lift coefficient, basically how much lift it produces. And you can see that the circles are the normal airfoil in the normal direction, and the triangles across the board, which are better, are the airfoil pointing backwards. And in fact, if the airfoil had no thickness and was a flat plate, it would do better still, because at these low Reynolds numbers, the airflow doesn't like following curves. So what happened? Everyone did their early research with the wrong Reynolds numbers, and everyone thought that skinny, skinny, skinny wings were the right answer. So we have this effect. If one skinny wing is a good thing to do, then a whole load of skinny wings must be the optimum. Which leads me to our friend, Mr. Caproni, who was actually a successful aircraft designer and went on to design many machines. This is the Transaero or the Noviplano or the Campromissimo. His idea here was to cross the Atlantic with this thing with 100 people, and it could do the 100 people thing. It had a crew of 8. It had people operating the engines in engine compartments with basically semaphore signals and telegraph signals like a ship to command the engines. The thing could do 70 knots and had a range, unfortunately, of not quite transatlantic. It could go 330 miles, it turns out. It had some of the most powerful engines ever built at the time. You can't see them here, but it's got half a dozen engines basically at the front of these pylons, and I think it's got 5 engines altogether. I can't remember. I think it's got like 2 at the back and 3 at the front of the most powerful engines available. But what do you notice? Look at the Dragonfly airfoil sections. Well, when you make a wing this thin, it's catastrophic for a number of reasons. Number one, and I think it's really obvious, you have to brace the daylights out of it because structurally it has no strength at all to resist aerodynamic loads like lifting or twisting loads, which all wings tend to produce a twisting moment as they produce lift. So what do we have to do? We have to add struts and bracing wires. This airplane had roughly 2,000 meters, 2 kilometers of bracing wires on it. roughly 1.2 miles for our friends in the States. So that's an awful lot of wiring. And you go, well, okay, so be it. So I'll tell you a little bit about what happened to this machine, then we'll talk about the aerodynamic consequences. It actually flew. It flew, and successfully, the first flight, they had a little bit of an uncommanded pitch up. They really didn't know much about the aerodynamics of something like this. This was, as you can tell, basically half a dozen airplanes that were basically put together from profiles that worked on a biplane before. But the aerodynamic and flying control performance and flying qualities were unknown, and it pitched up. On the second flight, they decided, I think, by rumor, to put ballast in the front to stop it pitching up, which worked well enough until the ballast slid to the back as it took off. And the thing pitched up again and then nosed over into the bay that it was flying over, which caused extensive damage, but not catastrophic damage until they hitched it up to a towboat that tried to bring it back to its hangar, where they succeeded in completely riding off the vehicle, absolutely destroying it. So it did have two flights, one shorter than the other. It does fly. There's no possibility ever of it crossing the Atlantic, just simply because they couldn't carry enough fuel because of the drag that had to be overcome to do this. This was the Spitfire of World War I, the SE-5A, Royal Aircraft Factory SE-5A, a very successful fighter. And again, it makes the point. Take a look at the airfoil section on the horizontal stab here. Once again, we're back in dragonfly territory. And of course, we need our bracing wires and our struts. And the effect of this is huge on the drag side of things. We'll see in a moment. As a comparison for roughly the same size airplane, this is, of course, the Extra 300, a very highly capable aerodynamic, aerobatic, I should say, vehicle. And you can see the wing thickness in comparison to this. Now, we'll go back to our friend the dragonfly, and I said this is what nature does at low Reynolds numbers. Well, what does nature do when the Reynolds number goes up a bit? Let's have a look at nature's perspective on a capable flying machine at higher Reynolds numbers and compare it to the dragonfly. There is no question that this airfoil has meat to it, pardon the pun. It has a very substantial thickness that goes far beyond the necessity. And you go, well, wait a minute, John, it has to be that thick to fly. No, it doesn't. Pterodactyls and bats and flying squirrels have membrane wings, and they all fly appallingly. And therefore, when flying is your bread and butter, so to speak, you can't stick with the membrane approach. So if we had looked around early on, and remember, we had these in the 18th century, we had the math to solve this, we would have decided that the wings needed to have this kind of thickness ratio instead of the dragonfly approach, but we didn't, as you saw from the SE-5 I just showed you. Now I'm going to show you a little bit about the effects of drag. We talked about laminar flow and so on and so forth, and Reynolds number, and we'll have a look at a couple of shapes that we know quite well. The classic one is the flat plate. In fact, if you go back to the SE-5, look at the front of the cowling there. There's a flat plate right there, right behind the propeller. So half the thrust of the propeller is just pushing against the cowling. It's a good thing because it cools the engine, but it's not great from a drag perspective. So there's a flat plate. A sphere actually has appalling aerodynamics. You'd think it's a very aerodynamic shape. It's an appalling aerodynamic shape. A sphere with a fairing, a stretched out sphere, is starting to look a bit like a wing shape. And a sphere and a housing is what we did struts to try and make them a little more aerodynamic. So let's have a look. Remember our drag equation had coefficients of drag. Let's take a look at some representative coefficients of drag. And to understand what these are, for something that's the same size as another thing, the coefficient of drag will tell you how much more the drag is, the relationship of the drag between the two objects. So take the first two here. A flat plate, edge on, has this coefficient of drag. A streamlined airfoil has roughly 50 times the drag of a flat plate. But the airfoil does a heck of a lot better than the flat plate at producing lift, so we take that compromise. And you can see where a typical car fits in. Here's where our ball fits in. Look at it compared to an airfoil, a streamlined airfoil. It's almost 10 times worse. It's 8 times worse to fly a ball. Okay, solid hemisphere. Sorry, it's a half ball, and this is a full ball. awful. But take a look at a wire or a strut, 1.2. So inch for inch, foot for foot, meter for meter, our airfoil has a coefficient of drag of orders of magnitude less than our wire or our strut. So although our forefathers thought that the wings were producing most of the drag on their SE5s and on their Capronis, the exact converse was true. Actually, what the engines were fighting almost exclusively was to haul all the wires and struts around. And the airfoils themselves were almost in the noise. Which leads us to a golf ball. I hope this video plays here. So the top one is a non-dimpled golf ball, and it has the laminar boundary layer, which gives up almost immediately. It just simply can't follow the curve around the top of the golf ball in the bottom. The dimpled golf ball, which you're all familiar with, see how the boundary layer is already turbulent well before it gets to the top? See how the little bubbles up here? I don't know if you can see my cursor, but up here. But that turbulent boundary layer, let me just see if I can play that one again. Well, I'll just hold it there. That turbulent boundary layer stays attached longer. It's difficult to see, but that wake is much thinner and less obstructive, if you will, on the dimpled ball. And if you want to compare it, just think of what it's like trying to hit a squash ball or a ping pong ball, a table tennis ball, compared to a golf ball. If golf balls weren't dimpled, all of your holes would be par 8 and up. The dimples aren't cosmetic, and they're not just about getting a better grip on the club. They're about making the thing fly. It's a very subtle difference, but that's what it looks like. In aviation, we have similar things. There are two effects here. These strakes that you see aren't anything to do with aerodynamics. They're Piper's inexpensive way of making thin aluminum or aluminium stronger. So these things are nothing more than corrugations to make the plate stronger. But these things on the bottom, they look counterproductive, but they are actually, they're called vortex generators, are there to trip the boundary layer. So the boundary layer tries to be laminar, and these things say don't be laminar. Why? Because a non-laminar turbulent boundary layer mixes more air and stays attached better. And this is an all-moving control surface, and it's more important that the airflow stay attached for the control surface to work than it is to have smooth laminar flow. Laminar flow is a holy grail that's very hard to achieve and very easy to disrupt. Even by putting flies on the leading edge will destroy laminar flow. If you walk up to an airplane, you can see where the manufacturers tried to keep the flow laminar and where they just gave up, simply by looking at where they use flush rivets and where they use domed rivets. By this point, they've given up on anything to do with the laminar boundary layer. You can see across the front here, there are no rivets, and there are flush rivets, I think, on the front here. But here, they're domed rivets. On most airplane wings, underneath, you'll see they don't bother with flush rivets because they're expensive and structurally a little more difficult. But on the top of the wing, on a jet particularly, they try and keep the wing as smooth as possible all the way across, unless they're trying very hard to keep the flow attached. So what are the takeaways? The wind tunnel results just don't transfer if you get the Reynolds number wrong, and it's a problem we have. And if you remember the Reynolds number equation, one way we can make the Reynolds number work in a small wind tunnel is by changing one of the other factors, the velocity or the density, to make the Reynolds number work out. Now, when we change those other factors, other things go wrong, such as transonic effects are all messed up if we change the velocity. But at least we can come up with something like what the airflow should be like. And it's because of this laminar and turbulent boundary layer. And this led, as we've seen, to horrible compromises. One of the things I didn't talk about when I talked about thin wings is not only do we need to strut brace them, but now we can't put fuel in them. And putting fuel in the wings of an airliner is one of the things that stops you having to make them massively strong, because the fuel resists the wings trying to bend up and join hands on top of the airplane. It provides wing bending relief. So fuel in wings is good. It actually, until you land when it's bad, fuel in the wings stops you bending the wings upwards or reduces the bending, and means you can make the wings less structurally intense. Also, if you're trying to put things like, if you're in a fighter plane, put things like guns and so on, If you have a membrane wing, you can't bury anything in there. If you have a wing with some depth to it, you can actually do that. So there are many disadvantages that led from having too thin a structure. I'm just going to pass through this very quickly, and it's a little ad for our own Bombardier, now the Airbus A220, used to be called the C Series. This is an example of the massive lengths we have to go to literally to reduce interference drag. This is not so much a fuel tank, although it has guts inside it, it has componentry inside it, but the main function of this bulge here is to give the airflow a chance to sort out what's happening on the wing versus what's happening around the fuselage. And you'll quite often see these kinds of fairings near where the tails join, the horizontal stabs join. Anytime there's a big structural join like this, you might well see a bulge like this to reduce interference drag. It's a very complicated thing to design, but it has big payback. So obviously they wouldn't put something as big as this on the airframe unless they had to. Now, sometimes you can conveniently put the wheels in here at the same time and you win two things at the same time, but primarily this is to reduce interference drag here. Let's talk about induced drag. Induced drag is drag due to lift. It's categorically a different beast than the other kinds of drag we've seen so far. We have airfoils are sucked into the air, basically. There's low pressure on the top, which is the main factor that makes your airplane fly. It's the low pressure on top, not the high pressure on the bottom, although there's a bit of both, that sucks the wing up into the air. Now, if you have high pressure on the bottom of a wing and low pressure on the top, those two will try and equalize. They can't do it wherever the wing is in the way or the fuselage is in the way, so the only place they can do it is the wingtips. That's where you've left an escape path for the air underneath the wing to spill over and try and equalize the low pressure on the top. Because of that, we only see this induced drag when we're producing lift, because that's when these pressure differences are high. And because of some of the mechanics that I'll go through, the induced drag reduces as you go faster. Unlike the other kind of drag, which is a function of the speed squared, the induced drag is inversely proportional to the speed. And another thing that stops induced drag in its tracks is ground effect. Ground effect is when you're within about one wingspan. Span is the distance from wingtip to wingtip across the airplane. If you're within about one wingspan of the ground, induced drag goes away or reduces significantly because the air no longer has that ability to curl around that it had. The ground provides a kind of a buffer that we'll see in effect in a minute. So here's the total drag of an airplane as I go from slow to fast, from left to right. And you can see the induced drag starts very very high and reduces. And the parasite drag, which is all the rest of the drag, goes up with the square of the speed. And the total drag has this shape here, which we call a drag bucket for obvious reasons. And the drag bucket, where the two drags are equal, is actually where the minimum drag happens. And because lift equals weight, the L over D, which is lift to drag ratio, is best because the lift doesn't change. It equals weight, more or less. So when the drag is least, the lift over drag is most. So this point where these two drags cross over is where we have the most lift to the least drag. And that corresponds to a number of important airspeeds for a pilot, not least of which that's the best gliding speed, because the glide ratio of your airplane is numerically equal to the lift to drag ratio. That's why airliners actually can glide a heck of a lot better than most light planes, because they are very clean, have very low drag. So a typical airliner can glide 150 miles from a cruise altitude. In fact, a normal descent for an airliner is a gliding descent in essence. So if you have a lift to drag ratio of 20, which is not atypical, that means you can glide 20 miles for every mile you are up. So you can go 20 miles for every 6,000 feet. Another interesting thing about this curve is if you go slower than this drag point here, this minimum drag point, look what happens. The drag goes up. So what happens here is it takes more thrust and hence more power to fly slower. And that means that below this region, which is where a lot of airliners come in on approach, and certainly many fighters come in, the airspeed is unstable. If you go slow, you have to go slow. You need more power to go slower, and so you'll slow down more, which needs more power, and you'll slow down more. This was I used to fly one particular little airplane, the F5 or the T-38 to the Americans, or roughly equivalent. We used to do air-to-air refueling, and we used to do it behind a C-130. And we'd be operating our F5 down here. The C-130 would be operating here as fast as it could go. And we'd be going about as slow as we could go. We could just hook up to the fuel hose. What did that mean? Well, our drag was enormous. In fact, it was so enormous, we had to fly in afterburner on one engine to stay slow enough to keep up with the Hercules. We had to fly in afterburner on one engine to fly slowly enough to keep up with the Hercules. We didn't have afterburner in both engines because it was too hard to control. Remember, you're trying to fly accurately to within a foot or two. And so what we would do is we would put one engine in afterburner and then use the other engine in military power to do the formation flying. And because the engines were close together, it didn't throw us off too much. But it meant that effectively when you were refueling from a Herc, all you became was a giant fuel transfer unit where the fuel would go from the Herc to the F5 and come out as smoke out the back. And you would barely gain any fuel because your consumption was so high. So it was good for practicing refueling, but not very good for actually extending your range at all. Here's the induced drag equation. Induced drag coefficient, directly proportional to the lift coefficient squared. Pi, God likes pi. It shows up everywhere in all kinds of equations. You wonder why on earth. It's because actually it's a trigonometric effect that we'll see in a minute. AR is aspect ratio, how long and thin the wings are compared to their breadth, the chord line. So you'll see, I'll show you pictures in a minute. And then this is an efficiency factor. So as you can see, as the lift coefficient increases, which happens when we go slower, the induced drag increases. Big is worse. And as the aspect ratio increases, as the wings become skinny and with very large wingspan, the induced drag decreases. And also, if we can make this efficiency factor good, we reduce the induced drag because the smaller it is, it doesn't go above 1 typically. The smaller this this efficiency factor, sometimes called the Oswald efficiency factor, the smaller it is, the bigger the induced drag comes. So we want to keep this factor down low. And this factor depends on the shape distribution of the wing. And it turns out that the optimum distribution based on trigonometry is elliptical. The optimum lift distribution span-wise is elliptical. So I've drawn a couple of ellipses on a piece of paper. And that gives us, by the way, an efficiency factor of 1 when we draw the perfect shape. So here's a pair of ellipses. They're identical ellipses, except their semi-major axis is a different length. And this is an optimum shape to reduce the induced drag by keeping the efficiency factor close to 1. And I think you all know where I'm going with this. All the historical buffs will know where I'm going with this immediately. R.J. Mitchell, who designed the Spitfire, was an absolute adamant believer in optimizing this. And this is those pair of ellipses. Notice, by the way, it looks like some vortex generators here. I'm not sure if that's what it is, but I think it could be. But certainly, you can see the elliptical form of all the control surfaces in an effort to reduce the induced drag. Notice it's a big fat airfoil. Gone are the gossamer wings that we had before, which means we can now put weapons in it. Here are the machine gun ports here. And we can put fuel in it should we choose to. The Spitfire had its fuel in the fuselage, but we could put fuel in here and reduce our wing bending. The Germans were not out of the picture either, but they were a bit more pragmatic. They said, yeah, it's good to have this optimum factor, but why don't we just provide the taper, but build something that's a heck of a lot easier to mass produce than this beautiful artistic rendering here. And so they used straight lines wherever they could, which made the mechanics of mass production a heck of a lot easier. And then they said, we don't really care about the induced drag coefficient of the tail. The whole thing is only there to keep the thing right way up. So I won't be as pedantic as RJ was here. So it's a bit less than a 1 efficiency factor, but it achieves more or less the same aim while achieving the compromise of structural manufacturing ease of use. Kurt Tank, a brilliant aircraft designer in his own right. Now, we said induced drag is prevalent when we're flying slowly, and we want to climb is when we fly slowly typically, or when we want when we want to climb, we have to fly slowly because we don't want all the drags to increase. So when do you see very high aspect ratio wings? When we need efficiency at low speeds. And you can see what extremes we go to. Notice these wings also taper. And notice that we have winglets, which we said, well, we didn't say yet, we will say in another slide, reduce induced drag. Why? Because they interfere this curling over effect of the airfoil. You could achieve the same effect by straightening this out and making the wing even longer. You can imagine the structural aspect of this isn't that easy, but everything has to give way for high performance at low speed. Well, when else do we need that? In the military, if we're flying at very high altitudes, we can't fly very fast because typically the engines, the jet engines, don't produce much thrust. And this is the military equivalent. This is the U-2. The moment you see a wing shape like this, you know what the folks are after. They're after reducing induced drag. And you can see here an effort, whether these are ECM or fuel tanks or whatever, you can see they're trying to reduce wing bending by putting them out here. They're not out at the tips because although you could reduce wing bending a lot, the problem is now you add inertial effects that make the airplane give it handling difficulties. So there's induced drag being reduced in a military context. So when you can't make the wings any longer, what you do is you add these winglets, and they interfere with the formation of the vortices to the extent that in an efficient installation, they actually compensate for their own profile drag with the reduction in induced drag, so you get a freebie. You go, well, why don't they make the wings just longer, which is almost identical? And structurally, these are very difficult to compute because they have twisting effects and all kinds of other things. The answer is, on very large aircraft, 777 and so on, if you made the wings longer and longer, the airplanes won't fit in the gate. You simply won't be able to park them at the airport. So, Frederick Lanchester, look at the date, 1897, had already sorted out winglets, 1897, compared to the early 1900s when people were starting to fly. Herner, in 1952, came up with these, reinvented these, and you can still buy Herner wingtip mods for Piper Cherokees. And Richard Whitcomb, who's one of my aerodynamic heroes, popularized them in the 70s. Richard had a penchant for finding old ideas, reinvigorating them and reapplying them, and winglets was one of his. Brilliant aerodynamicist. We'll meet him again soon. So here's a winglet in action. I will say one of the things that people did was they started adding winglets to airplanes that plainly didn't need them. It's the same as when you see your K car with an airfoil on the back. It solves a problem that doesn't actually exist, and they were done for cosmetic purposes. But that's not the case with these aircraft. So you can see the beautiful aerodynamic and structural design to bring this into, to fare this in. And you can see how large it is, and you can imagine why it would be very difficult to make the wing this much longer and then have all these things parked next to each other at the gate. These things are not very subtle. They look tremendously complex, but all they are is aerodynamic fairings to hide the very complicated mechanisms of these flaps called Fowler flaps that extend as they go down. So there's a lot of guts under here, but all they are is fairings. We'll see these in a different context momentarily, but they're just there to streamline things for the flaps. Gulfstream has a particular thing against these kinds of fairings. So if you look underneath the Gulfstream, G4, G5, you won't see any of these. Whoever the chief designer is at Gulfstream, they won't have it. They simply don't want these fairings underneath the aircraft for aesthetic reasons. It makes the job of designing these flaps a lot more difficult. It reduces drag and it has a much cleaner appearance. But that's what these are for. Here's another example of winglets. I'm not sure what aerodynamic problem these are solving. We're going to have to wait a few billion years probably before these things evolve into something useful aerodynamically, but there's an alternative winglet design. Now, what happens if induced drag doesn't matter? The Soviet Ekranoplans were ground effect vehicles. Remember, ground effect is when we're within one wingspan, and these things were over water typically. They were flying boats, if you will. And if you get that close to the water, induced drag is not a factor. So Rostislav Alexeyev ignored aspect ratio, efficiency, and all kinds of other things, but achieved some amazing results by flying in ground effect. So we're going to look at the Economoplan, which is the largest aircraft I believe ever built, with a takeoff weight of over 1 million pounds. Makes the A380 look small, 60 feet longer than a 380. Let's have a look at this beast. First of all, everything we said about making a wing efficient has been thrown in the garbage here. The aspect ratio is effectively a half. I mean, well, it depends. It's actually 2. The wingspan is roughly twice the chord. There's no effort at taper, no effort at efficiency factor. Yes, there are kind of winglets, but that's mostly to get this thing off the water. You can see they have given up completely with any attempt at reducing induced drag, except back here. This thing, the tail, is out of ground effect, right? It's above 1 wingspan. Remember, this thing is as big as a city block, so this thing is way off the water. And notice that all of our friends, many of our friends that we've seen already are back in action. We see the taper, the thin airfoil, the aerodynamic profile, as opposed to this thick, stubby, non-aerodynamic airfoil. See these 10 engines on the front? 8 engines, excuse me, on the front. If I read correctly, these things are only used to get it off the water, to blast in trained air over the wing to get it lifting early so it can get out of the water and stop having all the hydrodynamic drag. These tiny little engines back here are what keep this whole skyscraper-sized vehicle going once it's airborne, if you will. I've got a video of the thing flying. I hope it works. It's very fuzzy because I don't know what the source was of this. So here's this thing flying. Proves it does fly. You can see the effect of the winglets here, effectively stopping the vortices from developing. There's an idea of the scale. Notice the huge aspect ratio of the tail. These engines are firing right now, but allegedly what will keep it flying is just the little engines on the back. So I have another video here to make the point about induced drag and winglets. It's quite convenient. Just see if I can. It's quite convenient when nature gives you a way of visualizing vortices, which it does when it's humid, because the reduced pressure over the wing causes the air to condense out. As you can see on the top surface of the wing, there's the wing giving a lift, the top surface, see it all sucking there. Look at the vortices being shed, and watch what happens when it touches down. It's still going the same speed, effectively. No more vortices, no more shedding of vortices, no more induced drag. Now you can see all the spoilers because we want some more drag and we want to get the weight of the aircraft on its wheels. And some more drag by the engines reversing. So that's induced drag getting unwound. That's why when they teach us how to avoid vortices, they say, make sure you are on the ground past where the point where his nose wheel touches down. In other words, overfly him and land here. Or if he's taking off, make sure you are airborne and above his flight path before his nose comes up. Now here's a, here's a C5 flying over a mast. This is a NASA Langley video. And they've added smoke to help us visualize these vortices. I'll give you I'll ask you to guess which wing are we seeing the vortex off here. Well, it curls from high pressure to low pressure. It's got to be going around the right wing. So this vortex, there are tornado strength winds here, I should say. If you get caught by one of these, this will take a DC-9 and flip it upside down. We've got that data point. And it's not just C5s that do it. Here's a little ag plane demonstrating a wingtip vortex in action. These things are monumentally powerful. And when you're flying formation, you do what you can to not fly into them. It's flying into one of these that took down the XB-70 Valkyrie when the Starfighter got caught in one of these. It'll just flip you over on your back and then put you into it. So you can see it's a very profound thing. You can see two effects. One is it's pushing the air down everywhere across the wing, the back of the wing, and that tilts the lift vector backwards because it's perpendicular to the average airflow. That's why the longer the wing you have, the less this vortex affects you. That's why aspect ratio is so important, right? So that gives you an idea of the scope of these vortices. They're enormous. The second thing is your little engine up here, this little propeller, are what is driving this thing through the air to create this mess. So clearly, it's not a very efficient use of your power to generate 2 tornadoes behind you and drag them along everywhere you go. All right, now I'm going to address another lie that most aerodynamicists just take for granted, courtesy of the University of Cambridge. This is what we think happens to the airflow in a wind tunnel. No, this is what we see it doing in a wind tunnel. Nice parallel streamlines of air hit our airfoil. Notice the boundary layer, it comes across laminar, and then eventually you'll see it thickens and then it separates. The first thing is the air does not go faster over the top of the wing because it has to catch up with the bottom air, which has a shorter path. You'll actually see they don't catch up with each other. They don't synchronize. Right? There is no way that this is synchronized with its partner here. So that explanation that the air goes faster over the top because it's got a longer way to go, that doesn't wash. The second thing is you see the air, you see all these happy air molecules in these striated laminar air, layers, and you can see how the airfoil lifts. We'll see the angle of attack go up. The pressure gradient is adverse, it's bad, so the molecules have more and more trouble staying attached to the wing, starting at the back and moving forward on this particular airfoil. And you'll see it's separated here, and eventually the whole airflow lets go and goes, I can't do anything anymore. And in fact, in this region here, you will eventually see air flowing backwards, curling back and flowing the wrong way up the airfoil. Now, why is this picture wrong? Sorry, getting to the next slide is always a challenge with these things. Let me just go over here. This is the only website that, unfortunately, I've got a link to, and it's not alive anymore. But let's hopefully it will work. Okay, what really happens? Before this Russian whatever fighter comes in from left to right, the air molecules aren't flowing in nice layers at all. They're doing what you and I do when we're on a picnic. They're just sitting still, enjoying life. And then this bluff body comes hurtling by and disturbs the air molecules. At the end of the day, some of the air molecules will be left where they were. Some of them will be moved forward a bit. Some of them will be moved backwards a bit. But on average, they'll be roughly where they started. There is no flow from front to back in terms of a reference frame that's, someone sitting in the grass watching this airplane go by. Now, what happens when this airplane comes hurtling by is the air molecules send out a cry of alarm to all of their buddies. And the only way they can do that is by vibrating and bashing next to their neighbors and propagating a panic signal to all the other air molecules in front that this beast is coming by. And it's exactly as we would do if someone came rattling through our picnic with a bulldozer. And the air molecules do that. And the signal that they send by bashing into each other moves very, very fast and gets ahead of the airplane and tells all of the other air molecules that this disaster is about to happen. The speed at which these air molecules communicate with each other, we have a word for. It's called the speed of sound. It's no different than when we talk. What are we doing when we talk? We vibrate air molecules and they are transmitted at the speed of sound to whoever's listening to us. Now let's look at this animation. Here are all these air molecules sending out their panic signal way ahead of the airplane that there's a big problem coming. And what that means is the air actually can start getting ready to get out of the way of the airplane well before it reaches it. That's why you see streamlines that are bending long in front of a subsonic wing. What happens when the vehicle itself starts to go at near the speed of sound, near the speed of propagation of these molecules? Well, just at the same time as they send the warning out, the airplane's already reached that spot. So there is no real warning to the molecules ahead of the plane. Well, what does that mean? For one thing, the airflow cannot adapt to what's coming. The streamlines can't start moving around the airfoil before the airfoil is actually there. And that's bad news. Not as bad as this news, which is when the airplane is going faster than the molecules. So a panic-stricken molecule sends out a cry of alarm, and by the time that cry of alarm has gone out anywhere, the airplane's already passed it. So the first thing the new molecules get is the cry of alarm. And then all of these other panic things that have stacked up saying something terrible has happened historically. And as you can see, these things all stack up at an angle, and the angle depends on how fast the vehicle is moving relative to how fast the speed of sound is. If you think about these circles represent 1 time increment the speed of sound, 2 time increments at the speed of sound, 3 time increments at the speed of sound. Meanwhile, the left to right is how fast the airplane is going in 1 time increment, 2 time increment, 3 time increments. As these things stack up, they generate what we call a shock wave. And this, because the shock wave is at an oblique angle, it's not perpendicular, it's called an oblique shock wave. Let's see if we can get to the next one. So a little bit of math. It's what I just showed you. The speed of sound is the radius of these circles that we saw. The velocity of the vehicle is here. This is called the Mach angle, and after Ernst Mach. And it's very straightforward. The Mach angle, its sine is 1 over the Mach number. So if your Mach is 2, its sine is half, so the Mach angle is 30 degrees. Well, do we know any vehicles that go at Mach 2? And can we get a picture of one as it flies by on an atmospheric day when we can see the Mach angle in action? The answer is yes. We can critique the photographer for not getting his f-stop right, but it's hard to get Concorde going Mach 2 and getting a decent snap. Now, these are shock waves, so it's not exactly the same Mach angle, but it shows the effect. You can see that they're roughly inclined backwards at about 30 degrees, and we know Concorde is roughly a Mach 2 vehicle. Notice, by the way, the wings are well behind the Mach angle. So the flow they see is behind these shock waves, and depending on whether they are strong shocks or weak shocks, under some conditions, that's a subsonic flow that the wing sees, even when the airplane is going at high speed. But traditionally, with these oblique shocks, this will be a supersonic flow that the wing sees. Remember, the wing doesn't know the airflow is, the air doesn't know the wing is coming. So everything that happens aerodynamically to a wing is completely different in supersonic flow than in subsonic flow. It's what decides lift is the changes in the airflow, the direction of the airflow, not the sort of the Bernoulli principle that we see. Now, this is a film of a shock wave in a very slow transonic airplane. Transonic means some part of the airflow is sonic. So you may or may not be able to see this. I hope you can. There's a shock wave that's going to form as the airflow accelerates, Bernoulli style, over this canopy, over this cowling. A shock wave forms just here. Jim, give me a thumbs up if you can see it on your screen. I don't know. Yeah, you can see it. Okay, so here's the shock wave. So there is obviously sonic flow. It's a normal shock because roughly it's perpendicular to the airflow. Let's talk about how thick that shock wave is. It's pretty thin. If you start with a sheet of paper, it's about 500 times thinner than a sheet of paper. So that gives you an idea of how thick a shock wave is. And by the way, when a shock wave goes by you on the ground, there are massive pressure and temperature changes on the other side of it. And what do we call that? Well, remember, it's just vibrating molecules that have all stacked up. It's a bang that we call a sonic boom. Okay, we're running a little low on time, but we're almost there. Wave drag and area rule. Auto frenzy, 1943. Richard Whitcomb once again. It's ideal if the cross-section of the aircraft changes smoothly from front to back, particularly aligned to the expected angle of these the shock cones that we're going to see. Here's an example of an aircraft. Its cross-sectional area is increasing in bumps and bulges, much like the space shuttle that we saw. And here's one that is area ruled, where as the wing starts to stick out, let's compensate by making the fuselage suck in to keep the overall shape from front to back smoothly progressing. Here's the F-102 prototype that led to the F-106. The only basic difference between the two is there's no area ruling on the fuselage here, and yet there's very pronounced area ruling here. Here's the performances of these two vehicles compared. Planned to go Mach 1.2, it could barely go supersonic. In level flight, it could not. When they added the area rule, the thing could achieve Mach 1.5. My favorite area-ruled aircraft is this airplane, the Hustler, the B-58. It is area-ruled in every way you can imagine. Look at the canopy and then the fuselage as it has this super elegant wasting to it right when the wing begins, right? But the engines are area-ruled, as so is this pylon. Everything, like, let's not add all 4 engines. We could have put all these engines in a row, all at the back, like Concorde. But no, let's slowly introduce the engines so that in an area-ruled principle, we're gradually increasing the area, and then we'll gradually reduce the area. And just as the wing ends, let's add a fin behind, not right where the wing is. So there's a beautiful area-ruled aircraft. Here's what happens when you don't area-rule. The Douglas X3 Stiletto, 2 engines with a pole at the back that attaches the tail, and we'll put the pilot right between the intakes. It weighed 21,000 pounds. It was designed to go 2,000 miles an hour. As you can see, it's clearly not area-ruled. Everything adds and stacks and then suddenly stops. And then, I mean, even to add insult to injury, when the boom is thinning out, we'll just slam a whole load of tail right at the very end to give the airflow just one more panic attack. Okay, it didn't even get supersonic in level flight. This airplane was just as fast as this airplane. And you could have your martini in first class in one of these. NASA somehow convinced people they needed a Coronado, the world's fastest civilian airplane before Concorde. And you can see area roll in effect. These are Dietrich Kuchmann's, I hope I pronounce it right, I'm not sure, carrots. Their sole purpose was to ensure this aerial rule transition. Notice, by the way, well, you can see the wing. Notice the engines are staggered again. They didn't have to be. This engine could be at the back, or this engine could stick out in parallel. And these carrots are interleaved with the engines. They're not in line with them. And they taper off elegantly. And just as the wing finishes, the tail starts. And just as the fin finishes, the horizontal tail starts. There's nothing that could have stopped them putting everything at once. By the way, here's a row of vortex generators to keep the tail airflow attached for the elevators. Dietrich actually became famous. He ended up helping co-design Concorde's wing. Brilliant aerodynamic feat, which I can't get into this time. Another nice application of area rule is the 747. You've seen this before. The hump is not cosmetic. I mean, I've heard reasons that they thought it would be a cargo plane so they can make the nose open. That might be true. But clearly, area rule is happening. Look where the hump ends, just as the wing begins. And then we slowly introduce the engines. And as we start to taper the fuselage, we have to taper it so that we can rotate to take off and land without bumping the tail. We'll start introducing the fin, and as the fin starts to thin out, we'll start introducing the horizontal tail, and then we have a bit of a fairing at the back to finish things elegantly. Wave drag and wing sweep, for reasons that are just beyond me, we can fool the airflow by making our wings bend backwards, so that the only part of the airflow that contributes to the drag that we see is what's perpendicular to the leading edges. So we kind of trick the air into ignoring this span-wise component by sweep back. And the Germans were very good at this in World War II with the Me-262, but it gives you an idea of just how swept back the wings can be. And again, you can see the area rule in effect, and you can see the interference drag being addressed by this big belly fairing here. And you can see, again, these are not Kuchmann's carrots, but they are flap track fairings. We've given up on any kind of smooth flow by this part of the underside of the wing. And of course, winglets, which are there to reduce induced drag. And again, high aspect ratio, again, to reduce induced drag in the high altitude cruise environment. Almost done. Just to show that Burt Rutan, one of the real pioneers of our era, came up with this completely innovative drag solution to get SpaceShipOne back to Earth, whereby he uses this pivoting wing assembly to produce enough profile drag to achieve the re-entry for this instead of parachutes and everything else. And then they tuck it back away and make it a normal wing, which this thing can land with. Truly innovative piece of design. Not usable for high orbits, geostationary orbits. It's just too much energy to dissipate this way, but it's certainly usable for the low Earth orbit like SpaceShipOne and 2. This is the picture that's been behind me all the time. It's our own aircraft that we had at the company, one of the nicest aerodynamically designed aircraft ever. The only point I'll make is that not only is this completely smooth, even to the cabin windows here, the cockpit windows, 25% of the whole lift of this aircraft comes from the front door forwards. This little area here, just by the design of the fuselage shape, you can see the whole fuselage is a lifting body, and you can see the aspect ratio of the wing is enormous. It's a very long, thin wing. It looks more like a popsicle stick. So I just have to recognize one of my colleagues who departed us earlier this year, who came up with these quotes. If you can walk away from a landing, it's a good landing. But I like part two, which is if you can use the airplane the next day, it's an outstanding landing. And of course, that is the famous Chuck Yeager, who broke the sound barrier and overcame the transonic drag that was thought to be an impossible one to overcome. So good for you, Chuck, and we miss you, and thank you for your contributions to our trade. So that's the tail end of the Avanti, by the way, but that brings us to a close. I'd like to thank everyone for attending, and our companion societies, CASI, AIAA, and the rest for supporting this. We had more than 400 registrants for this, so we're delighted at the support you had. I hope you've got something from this lecture. It's hard to pitch to such a diverse group and hit everyone's level at the same time, so I hope that there's something for everyone. If you have any feedback, please send it to the Montreal at aerosociety.com, and we'll hand it over to Fadi, I should say, in just a moment for questions. Thank you for your time. Thank you for your signups, and we'll hope to have many more. The next lecture I've got in this series is on the history of human factors in aviation. If you'd like to see that one, drop us a note to that effect at Montreal at aerosociety.com. And I can't emphasize enough that the other groups, CASI, AIAA, and others, have an amazing lecture program that I strongly encourage you to support. I really enjoy every lecture I see with these folks. So thank you again. Fadi, over to you, sir, and we'll try and take questions. I'm here for as long as people care to ask questions. You're on mute, I think, there, Fadi. Nope, still can't hear you.
Oh, sorry.
There you go. There you go.
There we go. That was a wonderful lecture. Thank you very much. I'm not going to get into all the things that I've learned, which was quite a bit, because we have quite a lot of questions. We'll try to get as many as possible. So how we'll do that is, if you haven't had a chance to ask your question yet, feel free to do so. If we don't get through to them through the live, we'll try to answer them following that, if you put your contact information, if you're anonymous. So what I'll do is I'll ask the first question, and then I'll turn it to you, John, and then I'll let you stay on as live, and I'll kind of just be a voiceover with the questions. So the first question was, how do high aspect ratio wings reduce induced drag?
Okay, excellent question. Remembering the vortices that you saw on the wings, the simplest way to think about it is the further away you can make the vortex from most of the wing, the less influence it has. What the vortices actually do, aside from being a waste of energy by just spinning air, they actually tilt the airflow down, because they're a downwash. If you think about where the vortex goes behind the wing, it's pushing down on the airflow. And because lift is defined as perpendicular to the airflow, pushing down at the back moves the lift vector backwards, which is drag, induced drag. So how does aspect ratio fix that? You simply get the vortices as far away as possible. One way you could eliminate induced drag completely is what we do in wind tunnels, which is we put huge end plates that stop the vortex dead, or make the model extend to the edge of the tunnel. Now the vortex can't form, and you can't have any induced drag, and what we call that is two-dimensional flow. So the longer the wing, the further the vortex is from most of the wing, and if you could have an infinitely long wing, the induced drag would be negligible. Does that answer the question?
Perfect. Next question we have, any comment on the SME coefficient?
Oh boy, if we're going to get technical, I ask me a more specific question about it, and I'll try and get back to it, because on the aerodynamics, it's a little bit more difficult to get technical. What is it that we want to talk about?
We'll see if
we'll come back to that. Yeah.
Yeah. The other question, do you have anything to say about the solar-powered plane that went around the world?
Okay. I know of it. I'm not in a position to comment on solar power in general, but specifically, but I'll give you some very simple understanding of solar power. We know the energy flux coming from the sun, right? It's a fixed number, okay? It is what it is. There are so many, you could call it, calories, BTUs, whatever you want to say, coming from the sun per square foot meter of impingement on the planet. We know the efficiency of solar cells, and even if we took that efficiency to 1.0, so that, which we don't have, but if we could convert every photon of solar energy into electrical energy, let's say, and if we were to power fully efficient electrical engines, electric motors at 1.0 efficiency, we are still nowhere near being able to run an airliner with existing aerodynamic technology. At the lift to drag ratios that we have, which can be 12, 20 to 1, we simply cannot get enough energy solar-wise to power a realistic aircraft. So effectively, when you get these global efforts, what you're doing is effectively building one enormous solar cell, sacrificing everything to that, and structure, integrity, strength, everything else, because you've got to make it work, and then you can make something go around the planet. An incredible aerodynamic achievement, but there is no way, even conceptually, with current aerodynamic design, that we could power an aircraft by solar alone in any useful way.
Thank you. We have a question here. How much of this drag knowledge would have been known by Chuck Yeager when he broke the speed of sound?
Yeah. It's kind of interesting to me. Lord Kelvin is one of our most illustrious scientists. He's the one that gave us degrees Kelvin, right? And he went on the record as saying heavier than air flight is impossible, right? Now, if you just walk outside and look at all the birds flying around and bumblebees and everything else, I'm not quite sure how you can make that statement, right? Well, supersonic flight is impossible. We've known forever that bullets are supersonic, right? We have objects that can go supersonic. It's not like exceeding the speed of light where we don't have evidence of it happening and the theory says it's impossible. This is a case of where we had evidence, right? The two things that Chuck was up against were, I don't think it was the knowledge of the drag. I mean, we knew roughly what the drag did. We had real problems with understanding controllability. I'll see if I can get a picture of his rocket plane there, and I'll show you what I'm talking about. Let me see. Because you don't know what the airflow doesn't know what's happening ahead of a supersonic airflow. Let me see if I can find this here. There's one particular picture I want to try and show you. Okay, let's see if this works. Are you still seeing my screen there, Fanny?
Not yet, but I will share it.
Okay.
Your screen's live now.
Okay, you see the picture of the XS1 here?
Yeah.
The rocket plane with some ad that I can't do anything about for the moment. I just did this Google search. I hope it stays clean for the audience here, whatever it is. See the elevators on the back here? And this surface, it has no, here, get rid of it this way. This surface, the airflow coming over the surface has no idea that the elevators are deflected until the air physically rams the elevators, effectively, right? Under subsonic flow, well below transonic, the air is starting to adapt to these elevators being deflected way over here, and it's curving around, and effectively the elevators change the shape of the whole tail, and the air responds to that. Well, what happens when you're transonic or supersonic is the air goes, oh my gosh, and then slams into these things and then deflects. So the only control power you have is literally that tiny area back here. So two things happen. One is when you go supersonic, these things lose their effectiveness almost completely. Number two, the center of lift shifts from roughly quarter chord to roughly half chord, which means that the airplane becomes massively more stable and less maneuverable, which is a bad thing in this case. And number three, The shock waves that start bouncing around with all of this trauma that's happening start moving these surfaces around if they're reversible. So you get massive vibrations and buffeting of the stick and so on and so forth. Number 4, if the wing isn't very rigid, when you deflect one of these surfaces, the wing, because the air loads are so high, twists in the wrong direction, so you actually can have a reversal of the controls. So you move the stick left and the plane goes right. These combined effects caused a lot of the World War II fighters that were in very steep dives to avoid the bad guy, whatever, to lose control. And the lift shifting back makes the airplane pitch nose down and accelerate, and effectively they'd end up in a terminal situation they couldn't recover from. These are the things that this aircraft was trying to overcome. So they overcame them with short, stubby, stiff wings, immensely strong airframe. I don't remember, it was like a 9G airframe here. This was not a good idea. What they did was eventually, and you can see it has an element of all moving tail, but eventually they got rid of elevators altogether and just made the whole tail move, so that most contemporary supersonic fighters, just the tail moves completely. So it wasn't the drag that was difficult to overcome alone. Notice there's no area rule here at all. But it was this combination of aerodynamic and handling qualities issues that was the real problem. Okay.
Thank you for that. We have a couple of questions here from Eric and Ian about riblets. Can you address the use of riblets as used on the America's Cup racing yachts for drag reduction and any application to AC, so you mean aircrafts? And then, yeah, the other question is, will riblets make an impact in the future?
Okay, I'm embarrassed to say I don't know what a riblet is. So while we talk, I'm going to look up what a riblet looks like, and then I'll tell you if I have an opinion on it. Just give me a second. I mean, I know what the word means, but I don't know the America's Cup context. So just give me a sec, and I'll see if I can answer this in real time. So the first thing it says is NASA riblets. When I did a search, it came up under NASA. So it gives you an idea already, the connection with NASA. I've done a search on riblets, and I'm just trying to see where they physically are. So, okay, here we are. Okay, so what they seem to be doing is acting like vortex generators and swirling the flow. I don't know what they do, in a boat context, but the reason you swirl the flow, and the reason we have vortex generators, and the reason laminar flows are not as efficient as turbulent flows is laminar flows are A, easily messed up, and B, the turbulent flow, by swirling, brings in unaffected high energy air from away from the surface that you're interested in. So it sucks clean, high energy air into the boundary layer, which is the treacly, sludgy air that's normally near the aircraft surface. So I think what these vortices that these riblets are generating are a way of keeping the airflow attached better across the surface. And that's what we use vortex generators for. I don't see a clear picture on the boat to see where and how they're implemented, but from the close-in diagrams I'm seeing, they seem to be exactly the same concept as vortex generators. I see them shedding vortices, which is what they would do in aviation.
Yeah, one of the comments here was sort of like dimples on a golf ball.
Yeah, so anytime you have trouble getting airflow to follow a shape, laminar airflow is bad news. It has lower drag in general, but it's bad news for following a shape. Particularly in front of many older aircraft, in front of control surfaces, we'd throw, like a 707, we'd throw vortex generators out by the dozen to basically shake up the airflow, suck in the clean air from away from the wing, and drag it down and train it, as we call it, so that the airflow stays attached. So that's how that would work.
I think we have time for a couple more questions. They keep coming in, so I do apologize.
Well, I'll stay on as long as people stay on, and people will drop off in their own time. So, I mean, people have made the effort to sign up. I'll stay on as long as people want me to.
That's good. I recall being told there was an aerodynamic advantage to the Corsair's wing joining the fuselage at the right angle, as opposed to requiring a wing root fairing. Is that so?
Well, of course, I don't know because I wasn't involved with the Corsair, but the Corsair's design, the main governing thing about the Corsair was put as big an engine as you can strap a pilot to. It's an enormous radial engine that you sit the pilot on top of, and that way they can get the most performance out of it. The problem with an enormous radial engine is you need an enormous propeller to absorb all that power, right? And the problem with an enormous propeller to absorb all that power is you need an enormous undercarriage to keep the propeller off the ground. And the problem with an enormous undercarriage for a carrier aircraft is it's very weak, right? That if you have a long spindly undercarriage, it's very difficult to do carrier landings. So when you take all those compromises together, a cheap and nasty way, well, no, sorry, I apologize, it's not cheap and nasty. A cheap and simple way to fix it is to drop the wing down where the wheels are so that you can get the ground clearance that you need for the propeller with a very, very strong wing structure and the propeller and the short undercarriage. And then you want dihedral because which is the upslope of the wings. You want dihedral because it helps with the aircraft stability to some degree. You want some. And so what you do is you then, once you finish with the wheels, you then make the wings sweep back up. And that gives you your dihedral back. So I'll bring a picture of the Corsair up on the screen here, if I can find some pictures. Let me just find a decent one with the wheels out to give you a perspective. Everyone has all the pictures of this thing flying, so it's hard to find where the wheels are. Just give me a second. Well, okay, here's one. I'll bring this up in just a second, Fanny. Well, it's when you bring it up, it brings up every form of Corsair except the one I'm actually looking for. But can you see my screen still?
I'm sharing it again.
Yeah. Okay, so here's an example of the Corsair, and it shows the point here, right? Here's the enormous propeller. You can see it's barely got any ground clearance as it is. Here's the wing cranked down. Why? To get the undercarriage squat and strong. And here it is cranked back up, so I get the dihedral effect that is desirable, right? The wing is not cranked for aerodynamic purposes. It's cranked to get the gear closer to the ground. Now, whether the wing root fairing, it actually does join the fuselage at right angles, but that's not the explanation for the weird shape of this wing. It's to do with getting the wheels squat while keeping the propeller off the ground. And you can see that the propeller doesn't have a lot of ground clearance to start with. Next one.
Next question is from Diana. My ferry command research prompts me to ask if you can explain why the Liberator Davis was successful, or sorry, Liberator Davis wing was successful.
The Liberator had just like the P-51, a real effort at a laminar flow wing. Laminar flow intrinsically has less drag, all else being equal, than a turbulent flow wing. Because turbulence, right? What are you doing? You're effectively using engine energy to stir the air to basically froth the air up. So clearly, if you could avoid frothing the air up, that's more efficient. All other things being equal. Normally, air has stopped being laminar in the first probably third of the wing, going from front to back on the top. It gives up on being laminar, because the further back you are, the more the pressure is increasing. Because remember, it's very low near the front of the wing, where the suction is greatest, where the wing is gone around that leading edge curve. As the air goes to the back of the wing, the pressure gradient becomes adverse, and so the air molecules have more and more trouble going from front to back until they simply can't do it anymore, and they separate. And the inertial forces overcome the viscous desire of the air to stay attached, and it separates. So with heroic efforts, we can get the airflow to be laminar for maybe a half of the wing, maybe even 2/3. And that's what I believe the Davis wing was about. It also, let me just see, it was a Liberator, right? We're talking about.
Yep.
I will show you, just as an aside, the final exam at test pilot school, in the USAF test pilot school, is an oral where they show you a picture of a machine and they say, how would you test it? How does it fly? And they do exactly what I've done in this lecture. Is they would, you'd say, well, I think it'll fly well or badly, and then they ask you to come up with the equations. But the basic principle is how the airplane's looks reflect how it flies. Unfortunately, it's always really difficult to isolate one picture picture, but let me see if I can get this to work for you. All right. Let me see. Can you see my screen again? I'm sorry, I can't easily isolate. Well, what do you see happening here? Here's a tremendously high aspect ratio wing, right? It's really not far off some of the gliders I showed you, right? So if you combine the effort to make this wing laminar flow plus high aspect ratio, which means that bombers aren't very, very fast intrinsically. It's very efficient at low speed, or not low speed, at the speeds that it was designed to fly at. So you can see here the efforts. I mean, there are other bombers that had, you know, a completely different wing platform where it's much squatter and fatter and shorter. So that's how I would answer that question.
Perfect. Next question from Panos. Thanks, John. Excellent lecture. Do you have an estimate of the drag coefficient of the airplane behind you and how it compares to airliners?
Actually, I can give you a rough approximation, Panos, because the glide ratio of the airplane is published. I don't remember it, and I'll look it up while we talk, because I have that somewhere. It's very close to an airliner. It's probably slightly worse than an airliner because it has propellers. But to give an example, I flew that Avanti and I had to do an emergency descent on one flight. We had a windshield crack, and the emergency descent on the Avanti, there are no speed brakes, and you can't throw the wheels out or the flaps out at altitude. So the emergency descent is a 5-degree nose down flight idle descent, and that redlined the airplane. 5 degrees nose down, redlined the airplane. You know, when you think of World War II movies with airplanes in semi-vertical dives and so on and so forth, 5 degrees would take this airplane to its red line. So that gives you an idea. I will look up what the glide ratio was, but it's going to be very, very similar to an airliner. And I'll come back and just drop you the number, because the lift to drag ratio is numerically equal to the drag ratio to the glide ratio. So if we can glide 2 miles per 1,000 feet, we can fly 12,000 feet for 1,000. So it's 12 to 1 is the lift to drag ratio at cruise. So that will give you an example, but I'll look up what the actual numbers were in a minute. I'll take the next question, Fadi, and I'll look this up while we talk.
Sounds good. Next question is a bit more general. What is the general career outlook on aerodynamics related fields at the present time?
I'm not looking for a job this second, so I don't know what the real market is like, but there's a huge interest in a lot of very innovative aerodynamic areas. One is this urban air mobility thing, where people are really getting into powered lift, which is something that hasn't been explored a great deal other than outside of the pure research. That's powered lift is an interesting thing. All of these people, you know, Google and Uber and all the associated companies are studying that, and my company is actually doing a lot of work in that field to support them. Of course, space, the aeronautics of space, the SpaceShipOnes of the world. There's a huge movement in that direction, and aerodynamics is starting to play a part. You know, in the old days, it was, you know, you blast this thing up with the biggest rocket engine you could stick underneath it, and then you bring it back with as many parachutes as you can stuff into the nose cone, and plop it into an ocean, because you can guarantee you can hit an ocean from pretty much anywhere. That was the philosophy of Apollo. Then we did the space shuttle, and we tried to land it like an airplane, and now we're back into this, you know, hybrid of aerodynamics and so on. So I think the career options are very promising. You know, I don't know what they are right now. So just to go back to Panos, it'll do 2.3 miles per 1,000 feet, roughly. So what's 2.3 times 6? It's about, what, 15 or so? That gives you an idea of the lift to drag ratio of this airplane, which is very good compared to most airliners. Now, a good glider, like the one I showed you the picture of, achieves roughly a 50 to 1, 50 to 1. But, you know, not very good for carrying passengers and so on. Another note on the Avanti, if the airfoil ices up, and it is a very laminar or airfoil, you can't see a rivet. It looks like it's made of glass. It doesn't. You can't see a rivet anywhere. The glide ratio reduces by 50% if the airfoil has any ice on it. 50. Gives you an idea how laminar the flow is on the Piaggio.
Next question is from Al Jamal. Could you please comment on the research on creating variable cant angle winglets to reduce induced drag? Do you think it is a worthy idea?
I don't know the details. I mean, a winglet is just like any other piece of aerodynamics. It's optimized for one design point, right? If you're not interested in induced drag, if you want to fly at Mach 4, who cares about winglets? There's no winglets on a space shuttle. You don't care. So they're point designs to some degree. And of course, for an airliner, they would typically try and optimize the cruise point. So why would you have a variable winglet? Is to make it optimized for different conditions. Because most airliners, they typically cruise at one optimum point more or less. It may or may not be huge. Now, if you had a tactical aircraft that flies search and rescue missions where it has to loiter at very low speeds, but then has to dash at very high speeds, there I would see a point. And I don't know how effective this is in the research. I haven't got the data, but what you're always fighting is the trade-off of the complexity of the mechanisms. What if it breaks? What if one winglet goes and the other one doesn't? Running all the electrical or hydraulic or whatever lines out all the way along the wing to get to all this mechanism. And the actual fairing and blending of a winglet is a very difficult and complex structural and engineering design thing. So my answer to you is I don't know, but I would say that what will decide it is those trade-offs.
Next question is, do you see a role for lighter than air machines?
My company's involved with lighter air machines, and I'm one of the few folks that has actually dealt with the certification basis for lighter than air machines of late, mostly written by German airworthiness authorities, obviously for obvious reasons. As in any aviation vehicle, I've actually flown the Goodyear blimp. I actually have some lighter than air time. It's an interesting experience to fly one of those if you just flew a fighter plane the same day, which is what happened to me. The issue with lighter than air aircraft is we make many assumptions about them, and it's how do they work their compromises, right? How do they work the compromises of their enormous size, their handling requirements, the crew requirements to land them, take them off, to hangar them. There isn't infrastructure anymore. We have no more airship mooring masts. So you kind of have to hangar it. If you're going to have a gale, you can't just put a pair of chocks underneath the wheel and come back after supper and see how it's done, right? In the old days, they actually would, if it got too windy, moor these things on the mast and let them pivot around with the wind like a giant windsock. And the R101, which was the British airship that got lost, the Cardington R101, they actually let it ride out a very big storm with a bunch of politicians on board who got stuck waiting to fly it, and they couldn't fly, and they ended up pivoting around the mast as passengers. And the thing rode it out and survived. It absolutely would not have done if someone had tried to chalk it and hold it on the ground with ropes. These things have the surface area of a large ship. So you either need a hangar the size of a city or infrastructure. So they have a role. It's not an easy one. There isn't a lot of helium to go around. Hydrogen still makes us uncomfortable, but not to put them down. I mean, I think if they have a place, as we see from the Goodyear blimps that are still flying around today.
Next question from David. Are there any thoughts about the ways to quote unquote harvest and use the normally wasted energy of the wing vortex, much like is done with the brake energy in an electric vehicle car?
Regenerative energy. The easiest way to deal with it is you can make that vortex impinge on the winglet so that it basically overcomes the drag of the winglet completely, and then you end up with the benefit of the winglet in terms of the longer wing in other ways. There have been people that have actually done, maybe even patents, but certainly I've seen designs where people put a propeller that freewheels on the back of that vortex, and the vortex spins the propeller, and then you try and get electricity or propulsive power, whatever. The fact that none of those things has ever seen the light of day in a real airplane, to my knowledge, indicates that it probably hasn't been successful. I mean, for one thing, you're now adding complexity and all sorts of stuff. What is the efficiency? So basically what we do is we try and tailor the wing design to reduce that vortex as best we can and get our efficiencies that way. And we can reduce induced drag by just doing a good job designing the wing in the first place, right? That's probably where I would put my money.
Perfect. Thank you. And as we're approaching the 2-hour mark, I'm going to call it with a couple of more questions.
Sure. Yeah, sure, Freddie.
What does painting an aircraft achieve performance-wise? Weight up but drag down.
Painting an aircraft?
Yeah.
One of the primary reasons aircraft are painted is for corrosion resistance. So Eastern Airlines used to fly an unpainted fleet, and that worked for them. There are many materials like composites where you can have any color you want as long as it's white, and you have to paint it because otherwise the sunlight will get to the composite and deteriorate it. In terms of paint, in terms of smoothness, yes, it's important, although pure polished aluminum or composite is very smooth as well. An interesting field in paint right now is hydrophobic coatings. To prevent icing formation, which is a big bugaboo. Your efficiency goes way down. To give you an idea, there are some aircraft that are flying right now where 1 grain of sand or salt per square centimeter on the front of the wing, on the leading edge, costs you 30% of the lift of the wing. 1 grain of salt per square centimeter. So if the paint will stop that speck of ice adhering, you're 30% better off lift-wise. And if you don't have to blast half of the engine's output to heating the wing, it's a nice trade-off that you can have with paint. That's my understanding. There may be more sophisticated answers than that, but that's my understanding.
And for our last question, you were talking about the use of winglets. Some newer 737 have double winglets. What's the purpose of the second winglet?
The whole purpose of any winglet is to stop that flow, right? To stop that vortex, right? And again, it's a compromise, right? Why do you have a second one? Well, for one thing, you don't want to have just one alone that's enormously long, because it's now long and thin and has structural problems. Will it cause flutter? Will it break? Will it, so 2 small ones can achieve the same as 1 big one, and working together, their whole purpose is just to reduce that vortex. There's no magic about 2 small ones versus a long one. It's just a compromise of structures versus aerodynamic benefit.
Perfect. Thank you for that, John. Very informative lecture and questions. I really wish we had time to take more questions, but we are at our 2-hour mark.
No, absolutely.
So I want to thank everyone for joining us. I had seen one of the comments. We had someone join us from New Zealand. So we really did have a worldwide audience today. So thank you all for joining us. Thank you to John for a very informative lecture. For our co-hosts, Cass, it's wonderful to be able to partner with you and do something like this on behalf of the entire Royal Aeronautical Society Montreal branch. Thanks again. Our email is montreal@aerosociety.com. Please feel free to send us any feedback or if there are any further questions. Have the rest of your afternoon, evening, good morning, wherever you are in the world. And thanks again for joining us.
Thank you all.
Thanks. Goodbye.